Good evening, students. This is Dr. K. Jadhav. Would like to discuss about Chapter 6 from the Process Dynamics and Control on Final Control Element and Controllers. In this chapter, we are going to discuss the types of pneumatic control valve, what is the range in between the works, and what will be the transfer function. Pneumatic control valve are classified into the two types. One is air to open control valve and the another one is air to close control valve. So this is the diagram for air to open control valve, which consists of various parts like all motors, spring loaded diaphragm, inlet for pressure, stem, plug, sheet and all body. So these are the various parts of the control valve which are used in thousands in the industries because it works on the pneumatic pressure. In air to open control valve, the pressure is increased from lower side. So you can see the inlet pressure from the bottom side. This pressure is applied on the spring loaded diaphragm. So this spring loaded diaphragm moves up. So this spring loaded diaphragm is connected to the spring, to the stem and finally to the plug. So all this portion goes up and the cross section available for the flow increases, due to which all get opens and the flow coming in from this wall is increases. So this wall is called as a air to open control wall. You increase the pressure, the flow get increases. This pneumatic control wall works between 3 to 15 psi. It works fully open when the pressure is increased to the 15 psi and it will be remain closed when pressure is 3 psi. So when pressure increases, slowly the diaphragm moves up, stem moves up, plug moves up, more cross section available flow and slowly the flow rate is increased. So when the pressure become 15 psi, it will be a maximum amount of flow taken place through this wall. Another type of the wall is air to close control wall. It works in opposite manner, where the pressure, inlet pressure is applied from the top on the spring loaded diaphragm. So it also works between the pressure of 3 to 15 psi. When pressure is applied from the top, this pressure lowers the spring loaded diaphragm, spring, stem and plug. So what happens that as pressure increases, the less cross section available for the flow. As you goes on increasing the pressure, a very small cross section is available for the flow. It means that if a pressure increases, the flow through the control valve get decreases. This type of the valve is called as air to close control valve. So you can see the different pressure conditions for air to open and air to close control valve. In air to open control valve, it is fully closed at 3 psi and it is fully open at 15 psi. But in case of air to close control valve, it is fully open, remain at 3 psi and it becomes fully closed at 15 psi. Now, if you ask whether we can convert air to open control valve into air to close, yeah, it may be possible if you invert the plug position into the wall sheet. Okay, you can convert air to open control valve into air to close control valve. So these are the all works for the process control. We know that the instruction or signals which is coming from the controller goes to the final control element. These control valve are used as a final control elements. So These signals coming from the recorder come controller through the comparator, it goes to the control wall in terms of the pressure and in terms of the flow. In terms of the flow, the output is coming from the control wall. So this is how you can control the pressure, temperature, flow, level and composition. Now we will study about the all characteristics. The relation between the all stem position and the flow through the control wall at the constant pressure drop is called as a all characteristics. Means what is the relation between the stem position and the flow provides you the all characteristics. These all characteristics are described in three different types. The in between line is the curve for the linear wall. The second curve is for equal percentage and the third curve for is for decreasing sensitivity. So if we plot the graph of fraction of maximum flow to the fraction of maximum lift, means what is nothing but the flow and what is its relation with the lift of the stem and plug is nothing but correlated by the all characteristics. These two all characteristics are inherent and installed. Inherent characteristics, this is a measure of theoretical performance of the wall. And this theoretical performance is classified into the three different ways. Linear wall, where the sensitivity is a constant. Equal percentage, where sensitivity is increases with increase in a flow. And the third type is decreasing sensitivity, where sensitivity decreases with increase in a flow. So it's very important to know about what is the sensitivity. Sensitivity means it is y by x. It is a dm by dx. Means it is a fraction of maximum flow to the fraction of maximum lift. So this is the sensitivity, and this sensitivity describes the inherent characteristics. Whereas installed characteristics is depends upon the ratio of pressure drop to the wall to the pressure drop across the whole process line installation including the wall. So it is a ratio of a pressure drop is given by the installed characteristics. Linear sensitivity handling the entire system of pressure drop, then it is called as a installed characteristics are also be linear. If you want to calculate the wall size, then this is a simple equation used to find out the size of the control wall in terms of the capacity. Q is equal to Cv into square root of delta PV upon specific gravity, where Q is a flow rate, which will give you in gallons per minute. Cv is wall coefficient. Delta PV is a pressure drop across control wall when it is a fully open, and that value is in psi. So above equation is used to calculate the size of the wall by knowing its flow rate. Now in case of control wall, it is important to know how to calculate its transfer function. So we'll discuss about how to calculate the transfer function for the control wall. This pneumatic control wall is used as a final control element. It receives the signal from the controller and it gives output to the process. So if we discuss earlier control wall mechanism for continuous stir tank heater, okay, then the signals are coming from the controllers in terms of the electricity or current, and the signals going out from the pneumatic control as nothing but as a heat. So that heat is added to the stir tank. So we are going to discuss how to find out the transfer function for this pneumatic control wall. Generally, the pneumatic control wall is considered to be a first order system, and its transfer function is given by Q of S by P of S. Flow upon pressure is equal to Kv upon tau V S plus 1. So signals which is coming out from the controller or in terms of the current, these signals goes to the pneumatic control valve in terms of the pressure, and then the output coming out from the control valve is in terms of the flow. So flow is output from the pneumatic control valve and the inlet is nothing but the pressure. KV is a sensitivity or a steady state gain. It is nothing but the constant between the steady state flow rate and all top pressure. Tau V is a time constant for the pneumatic control valve, and in practice this tau V is very small compared to the time constant of the other component of the control system, and therefore the transfer function for the all is approximated to only kV, as tau V, if we consider, is very small compared to the tau P, that is the tau P is for time constant of the process. So in this case it is said that the control all is providing a negligible dynamic lag. Now what is the dynamic lag? Is nothing but dynamic lag means how is nothing but your control valve response immediately to the change applied pressure. Means if you apply the pressure from the top or bottom, and how much time it will take to change the flow rate through the wall motor. This nothing but lag is called as a dynamic lag. So this will be very small if you compare with the process. Now if we consider one first order system along with the first order pneumatic control valve, then this will be the block diagram. See how for pneumatic control valve it is kV upon tau Vs plus 1, pressure is inlet, flow rate is outlet. This Q, that is heat added or the flow rate, is not going to the process where it is kV upon tau V s plus 1 into y of s. Is it right? So if you want to calculate the overall transfer function of y of s by p of s, then you have to calculate by taking a product of y of s by q of s into q of s by p of s. Means take the individual transfer function, multiply it, you will get the overall transfer function for the first order pneumatic control valve and process. So it will be kV into kp tau Vs plus 1 into tau Ps plus 1. Now if you introduce the unit step change into the applied pressure, y of s become 1 by s into the whole product. Now you have to apply the partial fraction method. You have to introduce the unknown constant a, b and c. You have to write left hand side is equal to right hand side. You have to write the three different equations, and then you have to find out value of a, b and c. So this will be the value of a, b and c. You calculate these values by writing this derivation and put these values in the y of s. So you will get the equation such that whose inverse Laplace you can take. Now you can take inverse Laplace of above equation as y of s become y of t, kv kp remains same, 1 by s become 1, tau v upon tau v minus tau p becomes same, 1 upon s plus 1 by tau v becomes e raised to minus t by tau v, 1 upon s plus 1 by tau p becomes e raised to t minus tau p. So this will be the equation for y of t in terms of the pneumatic control valve. Now if we put this condition that tau v, the time constant of all, is very small compared to the tau p, then the above equation becomes y of t into kv kp as it is, and you see the second term 1 by tau v e raised to minus t by tau p. Okay, this term remain, and 1 by tau p into e raised to minus t by tau p, this get vanishes because the tau p is very large and tau v is very small. So that term get vanishes and you get this equation of kv kp into 1 minus e raised to t by tau p. Now if you write this equation in terms of the Laplace transform, in terms of the transfer function, then it becomes y of s by p of s is equal to kv. See, kv into kp into 1 minus e raised to t by tau is kp into kp upon tau p s plus 1. So what it means that, it means that the tau v value is very small compared to the tau p. Therefore only kv remains. Generally all time constant is one of the from obtained from the above equation, and it proves that control wall is a first order system and the dynamic lag provided by all is negligible. So this is how you can study the pneumatic control wall, which is of the two types, air to open and air to close. All these control walls works between the 3 to 15 psig. Sometimes the question arises, why not 2 psig or why not 16 psig? So my dear students, beyond 3 psig, if the pressure get reduced, or beyond 15 psig pressure increases, okay, there is no change in the position of diaphragm, stem and plug. So if you increase pressure beyond 15 psig, the conditions remain same, therefore flow rate does not changes, therefore there is no effect of increase or decrease in the pressure beyond 3 to 15 psig. All the pneumatic control valves which are used in the industry are work only between these ranges. So this is how these pneumatic control valves are used widely into the industries, where only a pneumatic, that is air pressure, is used, and accordingly the flow rate changes, and if flow rate changes you can control the remaining all parameters which are required for the process industries, like a temperature, pressure, flow, level and composition. So this is how you can control all these parameters and you can control the process. This is one video that I have prepared. The next video I will prepare and I will come and meet you soon. Thank you.